In this lecture, we're going to explore auto-type deduction in a little more detail. And we're going to start by looking at a simple example. Here we have a simple variable called some var. The type is double, and the value is a 55 inside. But we can do a statement like this and do auto x and initialize that with some var. When we use the auto syntax like this, the compiler is going to know that it has to deduce the type of whatever we assigned to this x variable. And in this case, it is going to deduce that this is of double type, so this guy is going to be of double type here. If we try to prove this to ourselves, we can print the sizes of these variables. Some var is going to have a size of 8 because it is of double type. X is going to have a size of 8 because the compiler deduced it to be of type double. And if we print their addresses, we're going to see that they are at different addresses. So these are separate variables. And basically in X here, we're going to have a copy of the value that we had in some var here. This is what is going to happen here. Okay, this is one example we're going to look at, but we have a few more coming. The second one is going to show us that we can have surprises if we try to deduce from a reference type. Here we have our usual variable some var. It is of double type as you see here. And we're going to set up a reference to this guy here. So we're going to say double reference some var ref. And we're going to initialize this guy with some var here. What we're going to have is a reference to some var. And we're going to be able to manipulate this variable here through this reference here. But if we go down and do a syntax like this with auto-type deduction, what is going to happen might surprise you. Y is going to be deduced to be of double type, but it's not going to be a reference. It's basically going to be a copy of the value that this reference here is referencing. And this may throw a lot of people off, and they might think because we are assigning a reference to this variable y, the compiler is going to deduce a reference. It's not going to deduce a reference, it's going to make it a copy. And we have tried to say that in the comment here, y is not deduced as a reference to double. It's just a double that contains the value in some ref. It's basically a copy of the value we have in here. And if we try to increment y like we do here, the changes we do in y are not going to be reflected in some var ref or even in the original variable here, because y is a completely separate copy of the value that we have in here. And you really need to know this. If you have a reference and you assign that to a variable which is doing auto-type deduction, what you're going to be making is a copy of the variable. Y here is not going to be deduced to be a reference. It's just going to be a copy. I really want you to understand this. And if we try to prove this to ourselves by printing this information here, you're going to see that it is consistent with what we are saying here. Again, y is going to be deduced to be of double type, so the size is going to be 8, but incrementing y is not going to change the value we have in some var ref or even in the original variable here. So if we go down here and try to print the addresses of the variables here, we're going to say that the address of some var and the address of some var ref are the same, but the address of y is going to be different. And even if we try to print these guys here, we're going to see that y has been incremented because we have incremented that here. So it's going to be 56.5, but some var and some var ref are not going to change. They are going to stay at 55.5 here. This is the message. Okay, so this is another example, and you need to be aware of auto-type deduction when you assign a reference like this. But what if we really want to deduce a reference correctly? Well, C++ provides a syntax to do that. You have to specify an ampersand symbol after your auto keyword here. And when you do things like this, this is going to deduce a reference. And you can go through that reference to do some changes on the original variables here. And if we try to print our information here, this is going to be consistent. Now, because z is a reference, it's going to affect the original variables. If we print z here, we're going to have a 56.5. If we try to print some var and some var ref, we're going to get the same value. We're going to get a 56.5. Because we incremented through a true reference, which z here is. Another thing I want you to know is that reference autotype deduction is going to conserve the constness of our reference here. This is a const reference, so this is going to also be deduced to be a const reference. And we can't go through p here to modify the original variable. If we try to do that, we're going to get a compiler error, and this is something you need to keep in mind. But please be aware that non-reference autotype deductions don't keep the constness, because it doesn't really make sense to enforce the constness because it's going to be making a copy anyway. It doesn't really make sense to enforce the constness here because q here is going to be a copy anyway. So it's a completely different variable which happens to have a copy of the value of IAMConst here stored in this variable. So we can modify it however we want, and we're not going to get a compiler error. Okay, these are a few things you need to be aware of, especially if you are doing autotype deduction with references. You need to be careful and know that what you deduce is either a copy or a true reference. Now we're going to head over to Visual Studio Code and actually play with us. Okay, here we are in our working folder. The current project is bare autotype deduction. We're going to grab our template files pretty quick, and we're going to put them in place 19.7 here. And we're going to open this guy in Visual Studio Code by dragging and dropping here. This is going to open our main CPP file, and we're going to clean it up a little bit, remove what we don't need, and we're going to close the left pane here. And the first thing we're going to look at is bare autotype deduction, and this is going to just make a copy. If you look down here, we are saying auto x, and we are assigning some var. What this is going to do is set up a completely different variable called x. Its type is going to be deduced to be double because some var is double, but that's going to be it. This is going to be a copy. It's going to contain 55, but if you try to print the addresses of these guys, you're going to be surprised to see that x is a completely different variable living at a completely different memory location. So let's try and build this. This is super easy to look at. The build is good. We're going to try and open a new terminal here. And we're going to clear and run Rooster. Now you're going to see that x has been deduced to be of type double because the size is 8 here. Okay, this is one piece of information we are interested in looking at. But the other thing is that the addresses of these two variables are different. And if we go down here, we're going to see that some var lives at an address that ends in DE8, and x lives at an address ending in DE0. Hopefully this proves to you that this is a completely new, different variable which happens to contain a copy of what we have in some var here. And I think we should also print these guys to show you that they contain the same value, even if they live at different addresses. I think this is educational. So we're going to say some var, and we're going to go down and say x, and we're going to say x. Okay, what is the problem here? Some var. We have a single less than sign here, and now Visual Studio Code should be happy. So we're going to build again and see that these guys contain the same value. Can clear and run Rooster. You're going to see that they contain the same thing, but they live at two different addresses. And this proves that auto x here is going to contain a copy of this value, but it's going to be a completely new, different variable. Let's comment this out. We have a few more things to look at. The next thing I want you to look at is autotype deduction with references. Let's make sure you see the entire code here. So we're going to set up a variable of double type. Let's make this double. And we're going to remove all these guys. We don't need them down here. We have a reference to some var, and it is going to be initialized with some var here. And we are trying to do autotype deduction on the reference here. One might think that because we are assigning a reference to double, the compiler is going to deduce a reference to double. But I hate to break it to you again, this is not going to deduce a reference to double. It is just going to deduce double. And this is going to be a copy of the value that we have in this reference here. And we can prove that through the series of outputs that we have here. For now, we're going to go through this together and try to come up with what is going to be printed when we run this program. The first line here is going to print the size of some var. Some var is of double type, so the size of this variable in memory is going to be 8 bytes. This is easy. Some var left is going to be a true reference to some var. Size of y is going to be 8 because it is going to be deduced to be double. So the size is going to be 8. That's what we're going to print. But if we try and print the address of some var, this is going to be the address of this variable here. Okay, we're going to print that out. Let's say that it is ABC, but it can really be anything. Let's say ABC123, just as an example. But it is going to be the same address. Let's say 0x here to mean that it is hexadecimal. In here, I think it is more similar. I think it is going to be more easy to look at like this. So if we go down here, we're going to print the address of our reference here. And the reference is a true reference to some var. We're going to have the same address printed out here. So we're going to say 0x. Again, this address is just fictional. The compiler is going to use whatever address we have in memory, but we're going to see this in a minute. And we need to bring in our semicolon back here for our code to be legit. If we go down here and print the address of y, y is going to be a copy, even if we are assigning a reference to it and doing auto-type deduction, but this is not going to deduce a reference here. This is going to deduce a copy or a double variable. If we print this address here, we're going to have some other address printed out. Let's say, for example, 0xAAB543, some random address. Anything you put in here is really going to do because this is just an example. And if we go down here and print some var, we're going to have 55.5. If we print some var ref, we're going to get the same thing, 55.5, because it is this reference here, which is referencing this guy here. But if we print y, notice that we have done an increment here. And what we incremented is really this copy that we made here. And this is just going to be 56.5. This is what we expect to get if we run this application here. Let's see if we are right. We're going to build with GCC. Let's bring this up and see if the build is good. The build is good. We can clear now and run Rooster. And we're going to see that we have 3 8s. This is exactly what we want. We have 2 addresses printed out and they should be the same. DE0, DE0. And we're going to see that the address of Y is going to be a different address than the other addresses. This proves that this guy was deduced to be a copy because this guy is living at a different address than the other guys. If it was a reference, it would be the same address. This is the message here. But we can go even further and prove this to really make you understand this. We're going to increment Y. And because Y is a copy, the incrementation here is just going to affect Y here. It's not going to affect all the other variables. And if we go down here, we see that some var is 55, some var ref is 55, but Y, which was incremented alone, is 56.5 here. I really hope you understand this. We're going to comment this out and look at another example. And in that example, we're going to find a way to deduce a true reference, because here, what we might have wanted is really to deduce a reference and be able to use Y to affect all these other guys here. But we're going to do that next. We're going to comment this out, so let's do that and go down and do another example. We are going to put in our code here, and you see that we basically have the same things, but what we are doing here is using a reference deduction here. We have an ampersand symbol after the auto keyword, and this is going to force the compiler to deduce a reference. Now, if we increment Z here, we're going to be affecting these guys because Z is a reference to some var here. That's what the compiler deduced. It is a reference and it is going to be referencing the same thing some var ref here is referencing. And if we go down and try to print these guys, we're going to get the data here. The first thing is going to be a double, so the size is 8. The second line here is going to print 8 because it is referencing a double type. Size of Z is also going to be 8. no problem here. But the addresses of these guys now are going to be the same. So let's grab what we used on top here. I don't want to type this again. So again, these are just examples of addresses we might use. The message here is that the addresses are going to be the same because these guys are references referencing the same data which is stored in some var here. If we try to print some var and some var ref and z, we're going to get 56.5 because this is a reference. It is going to affect all the other guys here because they are referencing the same thing in memory, if I can say it like that. So down here, we're going to get 56.5, and this guy is going to be 56.5 as well. And this guy is going to be 56.5. Let's do that. And we're going to build to really prove this to you. I don't want you to think I am making these things up. You can prove these things yourself. So we're going to clear and run roster. And now we see that the sizes are 8. The addresses are the same, and the values in those addresses are the same. And this proves that we are making a true reference deduction. And if you want to do a true reference deduction, this is the syntax you will have to use. Let's bring this up a little bit, and we're going to comment this out because we have a few more things I want you to see. The next thing I want you to see is that if you use reference autotype deduction, the constantness of your reference is going to be preserved. Here is a simple example to really drive this home. We have a double variable. It is constant. It is initialized with this value here. And down here, we set up a reference to that double variable. We're going to initialize that with some other var. And then we're going to try and do an auto type deduction with reference here. This is going to be initialized with our const ref. And we will try and go through that const ref and modify our data. Let's do that. We're going to uncomment this guy. The first 3 lines here are going to print our data, and we're going to attempt and print the data after our modification here. But notice the squiggly line, and this is a hint that we have a problem. And if we open our problems tab here, we're going to see expression must be a modifiable L value. What this really means is that the P reference we have here is a const reference, and we're going to go through it to modify the data that we are referencing. And the key message is that we were able to keep the constantness of our reference here through reference auto-typed deduction here. You really need to understand this, because if you don't, this is going to bite you in your daily job as a C++ developer. And these kinds of problems are really hard to debug if you don't understand these simple concepts here. That's why I am going through the trouble to really break all these little things down and make you see them and try them out on your own and really understand this. So this is going to give us a compiler error. We're going to uncomment this because we don't want this compiler error. And we're going to comment this out and show you that if you don't do auto type deduction with references, what you're going to have is a copy, and the constantness doesn't really matter anymore. We're going to show you that in a minute. Okay, we are going to go down and put in a simple example. And what we want to see is that constantness doesn't matter anymore if we are doing an auto type deduction without references. And that's what we have here. We have a simple variable. It is called imconst. The value is 71.2. And we are doing an auto type deduction here without references. But I think this is misleading a little bit. We should use a reference and try to deduce through that reference. So we're going to go down and say const double reference, and we're going to initialize this with imconst here. And we are going to try and deduce from this reference here. Let's say my ref. We can call it whatever we want. I am lazy. I am going to use my ref here. And it is what we are going to try and deduce from. So Q, even if we are giving it a const reference, it's not going to deduce a reference here. We have seen that. It is going to just make a copy, and we can increment this thing without a problem, even if we tried to really give it a const reference. We're not doing a reference deduction. If we try and use a reference deduction by adding an ampersand symbol here, we're going to get a compiler error. But if we take it out, we're not going to get a compiler error because Q is just a copy. So we can do whatever we want with the copy here, and the compiler is not going to mind. And this is really all I planned to share with you in this lecture. I am sorry it turned out to be lengthy, but it is going to be fundamental to the things we're going to be learning about in the next few lectures, where we're going to be learning about return type deduction with auto when we are using functions. Go ahead and finish up here and meet me in the next lecture.